Very good morning, students. Welcome back to second year physics. So in the previous class, actually, we finished about a related to magnetic flux, and here Faraday's laws, Faraday first law and second law is finished. Now let us, I want to say about a Lenz's law. See, in this Lenz's law, what is the Lenz's law? So the Lenz's law is nothing but it is actually fundamental law, and you remember it is a fundamental law, and here it is involving the law of conservation of energy. That means we know conservation of energy is nothing but energy can neither be created nor be destroyed. Say the conservation of energy is involved, nothing but there it is to be work is done, the work done are in the form of energies. That is a very important. That's what it is, a fundamental law, and here it is involving the law of conservation of energy, and here to help us, which one, this Lenz's law is help us to know the direction of EMF, to know the direction of current, and to know the direction of a current by using a Lenz's law. Sir, what is mean by Lenz's law? Here I'll tell you one thing. Lenz's law is basically, we can say like this. I'll show you a small experiment related to the Lenz's law. Suppose you say like this, let us you take a one coil, which is a circular coil. So that coil is at rest, and there is a magnet, it is north and south, which is placed like this. So both are at rest, you say magnet and the coil is at rest. So that here what happens, there will be a flux is flows through the given a coil, of course, entering the flux, but there is no change in flux. Is there any change in flux? No, there will be no change, because both are at rest. No, according to the Faraday's laws, what will happen? As long as the flux changes, that flux linked with the coils, therefore that creates the EMF and as well as the current. The phenomena we can call electromagnetic induction. Now both are at rest, of course flux is linked, but there will be no current and there will be no EMF. Suppose I want to say second one, you go for the same issue, north-south magnet, and there is a coil. Now the magnet is moving towards the coil. When magnet is moving the coil, therefore there will be what happens, the flux densities increases. That means electric lines of forces, intensities increases. Then what happens, there will be a north magnetic lines of forces are linked with the coil. Of course, as long as the flux changes, the flux linked with the coil, therefore the change in flux linked with the coil, there it is to be current and EMF is induces. But the Lenz's law gives us to know the direction, of current, and to know the direction of EMF. Now let us, I want to say, when north lines are, it is facing with the coil, no? Therefore this coil is behave like a north pole only. You write in this like a N symbol, you write, yes. So that it is facing a north, no? Therefore you write the end, you show a direction like this. So that it is showing the direction which is in the anti-clockwise. So you give the direction of current is or EMF is in ACW, anti-clockwise direction. Because the when north pole is moving towards the coil, no? Therefore the coil faces the north only. The coil becomes a north. So that now north is what happens, again the magnet is moving towards the towards a coil. Therefore the coil is also behave like a north, and the magnet and north both are in the same node. Therefore there will be a repulsion is act. As long as the magnet is moving towards the coil, therefore the coil is faces the north lines, therefore the coil become a north. Then there it is what happens, there is a repulsion is act between the coil and the magnet. Therefore EMF is induced because of the change in flux, but the EMF is always opposes the changes. The EMF is always opposes the changes caused by it, because the EMF is induced because of the change in flux only. There will be a change in flux. The change in flux is linked with this coil, no? Therefore that EMF is always opposes the changes caused by it. It's nothing but we can call as the Lenz's law. This is the Lenz's law. Lenz's law is stated as, see, the direction of induced EMF is always, that EMF is always opposes changes caused by it. That means this magnet is moving towards a coil, therefore because of the magnetic lines linked with the coil, there it is to be EMF is induced. That EMF only again it is opposing the changes, because again magnet is moving towards the coil, suppose there will be a flux density increases. Again the EMF is opposing the changes, but the EMF induced by the change in flux only. Now the EMF is opposing the changes. It's nothing but a Lenz's law. When magnet north pole is moving, sir, it is north is moving towards, no, suppose if the same situation I will show you, let us you take north south and there will be a coil. Now the magnet is moving away from, like it is, you say it is moving away from, you write as away and it is towards. Clear, no? Towards it is. Now it is moving away from. Now the magnet is moving away, no? Therefore this lines will come towards a north, because magnet is moving away from, no? Therefore this is coil flux densities decreases, because that flux flows towards a north. That means magnet is moving away from, no? When it is moving away from, there will be a flux flows towards the north pole or towards the magnet. That means again the coil is facing the coil faces the south, like it is behave like a south. Yes, you write a south S. That is, it is what it is, we can see, you write as like a south. That means now again the coil is opposes the motion of a magnet. In this also coil opposes the motion of a magnet, because the magnet is moving, no, it opposes, because of the EMF is always opposes the changes caused by. Now again also when magnet is moving away from, therefore this coil again opposes the motion of a magnet. That means this coil is behaving like a south, no? Therefore use this S letter and you write, you show a direction of EMF. It is in the clockwise, because south, end of the letter S, you write a directions, therefore the direction shows the EMF direction. Now the EMF is induced, no? Again the EMF is opposes the motion of a magnet, because this north and it is south, no? It is attracts. In the both the cases, one it is repels and the second one it is what happens, it is opposes. See, in the both the cases the EMF is opposing the changes caused by it. EMF opposes the changes caused by it, because there is a EMF induced because of the change in flux. That EMF is opposing the changes caused by it. One it is moving towards and one it is moving away from. Therefore both the in the cases what happens, EMF is opposes, because it is behave like a south. North and south is attracts, and here it is north, again it is repel. In the both the cases what is happening, that motion of a magnet is opposed by the EMF. There it is to be work is said to be done. In the both the cases work is said to be done, the work done which is in the form of energy. That's what we can say. In this case there is a law of conservation of energies involves. That's what I mean here. So when north is moving towards and north is moving away from, so that in case of north is moving away from, this coil is behave like a south. That's what EMF is in clockwise. And magnet is moving towards, therefore it is behave like a north. Therefore in this case anti-clockwise. Sir, suppose this is the first case, no? You go for the south. Yes, of course. You take south like north and there is a coil. Now the magnet is moving towards the coil. Therefore flux linked with the coil like this. Now the coil faces the, because the lines are south, no? Therefore this coil faces the south like, yes, you write like south. In case of a coil behavior like a south, no, there will be a current is induces which is in the clockwise. So look at again EMF direction, we can say it is a clockwise. Therefore when magnet is moving towards the coil, no, then it is faces the south pole. Then again the EMF opposes the motion of a magnet which is moving towards, or the EMF is always opposes changes caused by it. And second situation, again you draw a same south, north, there is a coil, therefore this coil is, now the magnet is moving away from the magnet. That means the lines of forces which are act towards like this. Now the coil is faces the what now, which is moving away from, no? Therefore there will be a flux densities decreases. When flux densities decreases, therefore the coil faces the south. Yes, of course. sorry, it is faces the north, I am sorry to say, it is away from, no, you write as a north it is. Therefore, when it is north and the direction of current will be what happens, which is in the anti-clockwise. So, EMF induced in this case anti-clock. Look at, both are same. See, in case of anti-clock, it is faces the north. Here also in this faces, it is also north in anti-clockwise direction. And these two are clockwise, which faces the south. So, the final conclusion according to the Lenz's law, as long as the magnetic flux changes and the change in magnetic flux is linked with the coils, therefore, there it is to be EMF is induces. That EMF is always opposes the changes caused by it. This is about what we can say Lenz's law. EMF is always opposes the changes caused by it. See, EMF induces because of the change in flux. Now the EMF, what is doing? It is opposing the changes. A change is which is changing here, magnetic flux is changing. That EMF opposing the changes caused by this we can call as the magnetic, Lenz's law it is. So, the Lenz's law we can say, and we can write like this, the Lenz's law. Is it clear everyone? So, that about a Lenz's law is over it is. Clear? And on the basis of Lenz's law and on the basis of Faraday's laws, see we have some, I think it is problems are there. We will see the problems. If any problems are there, then we will do the problems. Otherwise, we will continue. Of course, we did 1-2 problems in the previous class related to the EMF. Yes. There is a problem is there in the page number 273. 273 there is a one problem, question number 9.3. Right, look at the question which is given. See, a long solenoid with 15 turns. See, page number 273. Question number is 9.3. A long solenoid with 15 turns per centimeter. That means here small n is equal to capital N by L. So, how many number of turns are there? 15 turns per centimeter, no? So, centimeter we should convert into meters, no? That we can say 10 power minus 2. So, that 1500 turns per meter. And here a loop area is given, that is we can say 2 centimeters square. And here it is in given centimeters, no? You convert into meters, 10 power 4 meters square it is. Placed inside the solenoid normal to its axis. The coil is placed inside the solenoid normal to its axis. The coil is placed. This is the coil is placed and it is a normal axis. Clear? And come to the point is, if the current is carried by the solenoid, changes steady by 2.2 to 4 ampere in 0.1 second. There will be a current is changed, that is I2 minus I1 we can say, because the current is given as 4 minus 2, because I1 you take as 2. I2 is given as 4, so that we will get the 2 is a change in current. In time of what? dt is equal to 0.2 seconds, of course. So, what is the induced EMF in the loop while the current is changing? Induced EMF is asking, EMF is asking. This is the question mark. Of course, we know EMF is equal to d phi by dt. See, there is a dt is there, of course, but we don't know d phi, right? So, now we need to find a d phi. By using this, we can write as E is equal to d by dt of phi will be BA, because the flux is equal to BA, no? Yes, you write BA. And here we can write EMF is equal to A into, area is there, no? You write as A as it is d by dt of But B we know it is a solenoid given mu naught Ni you take. So suppose here I write E is equal to A into d by dt of mu naught Ni it is. So E is equal to A into mu naught N into di by dt. Here it is the like this. This is the final expression, right? This is what it is now, final expression which related to what? EMF induced in the coil. Here it is. Now we need to find this, no? Here the given we know, mu naught we know, and A we know. A is 2 into 10 power minus 4. Mu naught is 4 pi into 10 power minus 7. N is 1500. Di is nothing but a 2 by dt is nothing but a 0.2 seconds, of course, right? So let us, we need to calculate this. Okay, yeah, you take like this, it is 2 is cancelled, 0.10, 10 will come up, and here it is 4 pi into 20 into, see right, as 1500 into 10 power minus 7 and 10 power minus 4, no, 10 power you write as like 11, right? So better this you cancel, 4 into 3.14 into 30, right? Actually 300 we can, 10 power here it is 2 zeros is cancel, no, 10 power minus 10, again 2 zeros is cancel, 4 into 4 3s are 12, or 3.14 into 10 power maybe it is 7, no. So after simplify you may get the approximately the answer is related to this 7.54. See, after simplification 7.54 into 10 power minus 6 volt. So this is the way we should get the answer, by using a Faraday's laws or by using a Lenz's law. So this was given in the page number 273, page number, and 9.1 question number. Is it okay now? So this is the question. Clear? And you go through this. Again we have other also. See, I'll tell you the problems and numbers. So suppose you want to do it. Otherwise I'll also tell you. Okay, so this question, page number 275, question number 9.7, you do this. Okay, so that's all on the basis of this. So there is no other questions. Clear? So this is about a today's class, and we'll see in the next class continuation. Applications of Lenz's laws are there. So I'll tell you some applications on the basis of Lenz's law, at least 1 or 2 applications I'll tell you. Then after we'll move to the next one. Clear? Thank you very much. We'll see you in the next class.